Welcome to the Explainer. Today we're tossing the gut feelings, the fan bias, and all those usual emotions that completely dominate football debates right out the window. Instead, we're taking a highly analytical, incredibly sober look at the exact mathematical and statistical frameworks used to predict the 2026 FIFA World Cup. We are focusing purely on the data pipelines and those advanced prediction models deconstructing this upcoming tournament. Because let me tell you, this specific tournament presents literally unprecedented challenges for modern sports data science. Let's get right into it.
Okay, let's dive into this. We've got a really clear structure today. First, we'll look at the 2026 tournament complexity. Number 2, defining the prediction model. Third, the mathematical and feature mechanisms. 4, the innovation of continuous integration. And finally, number 5, the target audience and purpose. We're going to completely deconstruct this Dynamo-26 paradigm and modern machine learning pipelines.
Starting right off with Section 1, the 2026 tournament complexity, specifically the structural variables. We need to establish exactly why advanced modeling is an absolute mathematical necessity here, all thanks to the expanded format.
To really wrap our heads around this complexity, you just need to remember one number, 495. Because the 2026 tournament is expanding to 48 teams in a massive 104 matches, the rules for the knockout phase have completely transformed. Specifically, the best 8 third-place teams from the group stages will advance. And it's exactly this allocation of third-place teams into the bracket that creates literally 495 exact mathematical combinations for how the rest of the tournament could play out. The sheer volume of possible knockout paths is exponentially higher than anything we ever saw in the old 32-team format.
And this brilliantly illustrates why the structural complexity of 2026 renders traditional static prediction models completely insufficient. Classical historical forecasting relies on static point transfers, like the Elo system you might be familiar with, and they basically just calculate simple win probabilities. But those classical models, they literally buckle under the weight of this massive tangled web of 495 knockout combinations. To map a tournament with this level of structural complexity, analysts simply had to switch to dynamic machine learning pipelines. These give us highly flexible path modeling that can crunch through every single permutation.
Which brings us right to Section 2, defining the prediction model, and specifically the Dynamo-26 paradigm. Let's see what this model actually is.
Now, it's absolutely crucial to understand that Dynamo-26 is not just a single, rigid mathematical formula. Actually, scratch that. It's more like a living system. It's strictly defined as a whole family of data-driven, dynamic, adaptive prediction pipelines. What does that mean for us? Well, it means the system utilizes continuous reevaluation loops. It's specifically designed to handle the non-stationary dynamics of knockout tournaments. You know, those sudden, unpredictable spikes or drops in a team's performance. The prediction is a fully automated software process, not just a static spreadsheet.
To keep all this historical match data and Elo ratings flowing reliably, the model uses what's called a medallion architecture. It's basically a 3-step flow. First up is the bronze layer. This is where the raw, entirely untouched data like live match results are ingested. Then we hit the silver layer, where the data gets standardized, mapped, and cleaned. So making sure a team's name is spelled exactly the same across 5 different databases, right? Finally, we have the gold layer. This is the actual modeling layer, serving up perfectly prepped datasets with computed features ready for the algorithm to devour reproducible.
Moving right along to Section 3, mathematical and feature mechanisms. Let's look inside the algorithm's core and see how it actually calculates these probabilities.
Now, what's really interesting about this slide is that these models don't just lazily predict a win, loss, or draw. They actually calculate specific goal distributions. Football is historically a really low-scoring sport, which usually models nicely on a standard Poisson distribution. But there's a catch. Standard Poisson models systematically underestimate the likelihood of low-scoring dependent outcomes, things like a gritty 0-0 or a 1-1 draw. So to fix that, the model implements a Dixon-Coles framework. This essentially introduces a mathematical correction value to properly represent the stochastic dependence between two teams in tight, low-scoring matches. It's a total game changer.
But what exactly goes into these predictions? If we objectively break down the feature hierarchy, one dominant factor jumps right out: Elo differences. The sheer strength gap between two teams accounts for 39.2% of the model's predictive power. Right on its heels is form at 37.4%, calculated over a rolling window of recent matches. Then, context and neutrality, like the importance of the match and playing at a neutral venue, still holds a solid 17.6%. And here is the kicker. Head-to-head records, whether Nation A beat Nation B 5 years ago, offers a tiny 5.9% of value. Mathematically speaking, historical direct duels are practically just statistical noise compared to current form.
Once the model figures out the goal expectancies for a single match, it has to predict the entire rest of the tournament. And it does this by running an incredible 10,000 Monte Carlo simulation iterations. The computer literally plays out the entire 104-match tournament 10,000 times, pulling random outcomes based on those calculated probabilities. It takes that massive volume of simulations to successfully convert single-match goal expectancies into highly stable, reliable tournament advancement probabilities.
All right, Section 4, the innovation of continuous integration, looking specifically at CI/CD pipelines. Let's talk about what actually makes this new generation of models so revolutionary.
The real novelty here is the automated technological architecture. In the old days, we relied on pre-tournament static calculations. You'd run the numbers before the opening match, and those probabilities would slowly just decay and become obsolete as the tournament went on. Today, we use automated CI/CD workflows, continuous integration, and continuous deployment. This completely eliminates that static prediction decay because the system automatically recalculates and deploys fresh odds the absolute second the referee blows the final whistle.
Let's walk through this continuous calibration loop, because it's basically a high-speed chain reaction. Step 1. Data ingestion. The moment a match ends, live results are fed in. This immediately sparks Step 2, the pipeline trigger, completely automated via data version control. Step 3. Model retraining. The model physically retrains itself, instantly incorporating new parameters from the match that literally just finished. And finally, Step 4. A fresh Monte Carlo simulation fires up, recalculating all those massive tournament paths. The whole shebang happens mechanically without a single human lifting a finger. Let's move to and see how this builds. You might be wondering, how does the system adapt to mid-tournament structural breaks? Say a manager suddenly ditches a low block for a high press, or a star player suffers a major injury. Because this dynamic ingestion captures non-stationary dynamics live, it catches those sudden tactical shifts instantly. The pipeline doesn't stubbornly cling to historical data from 2 years ago. It heavily weights the reality of the tournament exactly as it is unfolding on the pitch right now.
And that brings us to our final segment, Section 5, Target Audience and Purpose. We've talked a lot about immense computing power, but let's look at the system utility.
To figure out the purpose here, we have to pivot our analysis and ask, who exactly utilizes these specific probability bands? Because knowing the end user completely changes how a distinct modeling system like this is built and presented. So the crucial point is comparing these commercial systems based on their respective audiences. Look at Opta. Their target audience is media and fans. So the primary output is digestible percentages, like telling you Spain has a 16.1% chance for the title. It's great for TV graphics. Then you have Gracenote, aimed at broadcasters and sponsors, mixing probabilities with demographic data for platform activation. But Dynamo-26, its target audience is pro analysts and betting syndicates. It skips the simple narratives entirely and provides incredibly precise probability bands and value deviation metrics.
For those professional data scouts and syndicates, just knowing who will win isn't enough. The Dynamo-26 model is built for identifying value betting deviations, literally finding the exact spots where true mathematical probability differs from the public market. It calculates highly granular under-over market probabilities. But even beyond betting, for professional clubs, this architecture facilitates completely objective, data-driven tactical adjustments and secures recruitment metrics that are totally free of any emotional scouting bias.
We'll leave you with this final, somewhat provocative thought. Research shows that top machine learning models eventually converge within a tiny 0.0011 variance ceiling. Basically, algorithms have hit the absolute limit of what historical data can tell us. Plus, these models statistically prove that in short knockout formats, defensive stability dominates over offensive brilliance. So, when you're watching the tournament, ask yourself, if top ML models converge within a 0.0011 variance ceiling, will the ultimate outcome be decided by the algorithm's data constraints or the incredibly unpredictable reality of on-pitch defensive execution? Thanks for joining us for this explainer. We'll see you next time.